Hello everyone. Tonight we're going to start our talk on the conservation of energy. So you've probably heard of the phrase conservation of energy. In a really formal sense, this just means that energy can't be created or destroyed. This means that in all of the universe, the amount of energy stays the same. It's just always shifting from one form to another. We can use this idea too, however, on smaller scales if we know how to define our system. So this conservation of energy can also be written in a mathematical way with an equal sign. Conservation can be written with an equal sign. So it looks like this. The initial amount of energy in a system has to equal the final amount of energy in a system. Now, if we look at the types of energies that we learned about yesterday, one of them was U, or potential energy, the energy that comes from lifting something up a certain height. I just gave the egg potential energy. So remember we wrote that with the capital letter U. And the other type of energy that we learned about was something called kinetic energy, or the energy of motion, of something moving. So these two initial energies, the combination of them, has to equal the combination of those energies as well, but in the final state. So before I lose you in this equation, let's start applying this to our real life situation. I think it's always appropriate to go back to Charlie on the hill. So there's Charlie on his longboard about to go down a hill. Okay, let's just say he starts from rest. So in the initial case, all of the energy is going to be stored in potential energy, or mgh. Initial. But because he's not moving, our 1/2 mv squared, our initial velocity is 0, so this whole term goes to 0. And then Charlie goes down the hill, and at the bottom of the hill, he has some energy of motion, or kinetic energy. However, all of his potential energy is gone. So if we rewrite this again, we have mgh final, but in this case our h final is 0. He has a height of 0, so that goes away. And he has all kinetic energy, or 1/2 mv squared. If we rewrite this, we get mgh initial plus, equals 1/2 mv squared. Oh, hey look, the m's cancel. And so we have an equation that describes Charlie going down this hill of gh initial is equal to 1/2 v squared, v final squared. So if we knew the height of the hill, we could find his final velocity at the bottom of the hill. And now the cool thing about energy is that it doesn't care what the situation is. You could easily apply this same scenario where there's potential energy transforming into kinetic energy into something like a pendulum, where you lift a pendulum up and you let it go and it swings down and has kinetic energy at the bottom, lifting up a distance of h. You could also apply it to a situation where you're dropping something off the roof and it's falling to the ground. Energy can describe all of these situations with a single equation. So to help us think about this idea of conservation of energy, we can utilize a tool called an energy bar chart. And this is how you make it. First, you want to set up using the equation for conservation of energy. Okay? In this case, we're just looking at potential and kinetic energies. So we're going to have U initial plus T initial is equal to U final plus T final. And what we're going to do is we're just going to draw a line over all of these. And we are going to make a bar chart, and we're going to trace the energy through this scenario that's happening. So we said initially Charlie starts from rest. So his kinetic energy here, his kinetic energy is going to be 0. However, we said that he's starting at some sort of height, so he's going to have a potential energy. And then we go to the final side. He's exhausted all of his potential energy, so U is going to be 0. But all of that energy has been transformed into the kinetic energy. So we can write the energy bar chart over here. So notice that the energy at the beginning, the energy is displayed by the height of the bar, is the same as the energy over here. The initial potential is equal to the final kinetic. So naturally, the next question that we have to ask ourselves is, what if there's rockets on Charlie's skateboard? How do we use these extra rockets? Do we use it in the potential energy? Do we use it in the initial kinetic energy? Do we use it in any of the final energies? Well, it all comes back down to our definition of work. Remember that when we do work, we give a system energy. So let's revisit Charlie on the hill. The first thing that we need to do here is we need to define what our system is going to be. So in this case, our system is going to be the system of Charlie and the Earth. I'm going to put this as a blue box around Charlie. So Charlie and the Earth are what is in the system. But now we have the rocket on the back doing work on the system. So we're going to have to alter our conservation of energy equation if we have an external force acting on the system. So we're going to rewrite this, except this time we're going to have the initial energy plus any work of outside forces, and that's going to equal the final energy. Okay, so we have our system. Our system is Charlie and the Earth. And we also have outside, and we're going to plug in the work from the rockets into that variable right there. So let's expand this equation once again, just like we did over here. We're going to get an initial potential energy plus an initial kinetic energy plus our work from the rockets, and that's going to be equal to all of the final energy. So our potential final plus our kinetic final as well. So before we move on, let's make an energy bar chart here of all the different energies. So we have some sort of height. Charlie is some sort of height above our 0 line. So we know that he has some sort of potential energy. Let's just give it 1, 2, 3, 4, 5 units. We know that the kinetic energy, let's say he's starting from rest, is going to be 0. We know that the rockets are going to add an outside force. They're going to add energy into the system. Let's just say that's going to be 3 units. And we know that at the end of the day, when Charlie is now at the bottom of the hill, now that Charlie's at the bottom of the hill, there's not going to be any potential energy. But all of the energy that came from his potential energy and the work done by the rockets has to be bundled up into his kinetic energy. So now he's going to have 1, 2, 3, 4, 5, 6, 7, 8 units of kinetic energy. So all of the energy over here, this plus this, equals that. And it checks out. So now we can expand this, looking at the energies we have and we don't have and plugging in further equations. So we're going to get mgh initial. Remember that this one is going to go away. We have the work done. Remember that work is equal to force times distance. So work is going to be force times distance. So let's say our engine applies a force of 100 newtons for 10 meters, whatever it may be. And we know that this term also goes away to 0, and we know that we're left with 1/2 mv squared, or a kinetic energy, and this is the final velocity right there. Let's say we know the height of the hill. Let's say we know the final velocity at the end. Let's say we want to figure out how much force our rocket applied. Okay, and let's say we know that it was on for a distance of, like I said before, 10 meters. So we want to solve for this guy right here. So first let's move this over. We're going to get force times distance is equal to 1/2 mv squared. That's the final velocity. That's going to be minus mgh initial. And then we have to divide both sides by d. And we're going to get force is equal to 1/2 mv final squared minus mgh initial all over d, the distance that the rockets were on. So we just found a force by the rockets. Imagine that I asked you to do the same problem only using forces, statics and dynamics of the last unit, and you had to include the curve of this hill. It would take a lot of brain power to do that. But by using energy, we can ignore the curve of the hill, and we can apply this equation to the situation without having to worry about that. So using energy is really advantageous in that way. Okay? So the last thing I wanted to do is just outline a procedure, much like I did last time, of how to solve problems like these. So step 1, you're going to define your system. Step 2, you're going to define the initial and the final conditions. So in this case, the initial conditions were Charlie starts from rest at the top of a hill with his rockets on, and the final conditions were his rockets were off and he had some sort of kinetic energy at the bottom of the hill. The third step, this part right here where we conserve energy and use bar charts to set up our equation. And then of course the fourth step is solve. This is where we do algebra and plug in numbers. And that's where I'm going to leave you tonight.